So let's talk about power series. A power series is a function of the form the sum n going from 0 on an times x minus a to the n power. So a power series is a function that looks like this. We've already seen functions that look like this earlier in our course. If, for example, an is equal to the nth derivative of my function evaluated at a over n factorial, then this is the Taylor series for your function f of x centered at x equals a. But I'm going to consider all possible functions you can get that look like this. That's what we call a power series. For example, I could have the sum n going from 0 to infinity of n times x minus 2 to the n power. That's a power series. It's centered at 2. A is called the center. So let me write that down. That's the center. And I have a power series. So the main question that you want to ask about power series is what values of x can I plug in to this function? Which values of x give me a convergent series? Which values of x divergent series? So let's give some definitions for this. So the interval of convergence, I, so I'm trying to describe what interval of convergence is. The interval of convergence for my power series is the interval of values for which the power series converges. It's the x values you could plug in. The radius of convergence R is 1/2 the length of the interval of convergence. So when we talk about power series, we also need to communicate the radius of convergence. The radius of convergence will tell us the interval of convergence and the values of x you can plug in. Okay, let's see an example. Let's find the radius of convergence R. Let's do it for this power series. Why not? So the sum n x minus 2 to the n. So at this point, we've built up a lot of machinery to decide whether a sum converges or diverges. When you want to find the radius of convergence or the interval of convergence, the first thing I would try is the ratio test. For these problems, the ratio test usually works out the best. So let's do the ratio test. Here's my answer. So when you do the ratio test, you look at a limit L. It's the limit as n goes to infinity of the an plus 1 term over the an term. In this problem, that would be the limit as n goes to infinity The n plus 1 term is this, where I plug in n plus 1 wherever I see an n. So I get m plus 1 x minus 2 to the n plus 1 power all over n times x minus 2 to the n. And I have absolute values here because some values of x might actually make the terms negative. Okay, so this is the limit as n goes to infinity. I have n plus 1 over n. And then these x minus 2 terms almost all cancel. They all cancel on the bottom, and 1 is left on the top. I still have absolute value. So the absolute value of x minus 2. Now, the limit of n plus 1 over n, that part's 1. So the entire limit is the absolute value of x minus 2. Now, if you remember the ratio test, what you do is you take this limit L, and if L happens to be less than 1, you have a convergent series. If L is bigger than 1, you have a divergent series. So in order for my series to converge, I want L, this limit, to be less than 1 to get convergence. This is where you get the interval of convergence. So I need the values x to satisfy this inequality to get convergence. So let's draw a number line and plot the values of x that make this true. There's my number line. Maybe here I have 0, 1, 2, 3, and so on. The inequality x minus 2 less than or equal to 1 says the x values have to be 1 away from 2. So the center of the power series is 2. The center of the power series will always be in the radius in the interval of convergence, because if I plug in 2, the center, x minus 2 is 0, and I get a convergent series. So the center is always going to be in the interval of convergence. Then the values of x are distance 1 away from the center. So everything in between 1 and 3. So this is my interval of convergence. It's all the values in between 1 and 3. And you might ask, does it include 1? Does it include 3 or not? It may or may not include the endpoints, but that's kind of irrelevant to decide the radius of convergence. So in this example, I really cared about the radius of convergence r. The radius of convergence is half the length of the interval of convergence. So the length of the interval of convergence is 2. So the radius of convergence is r, which is half the length, so 1. You might ask, why is the term radius applied to this situation? Well, if you have a center at 2 and you imagine drawing a circle with that center, the radius of the circle will be half the length of the interval. So the radius of convergence here is 1. Okay, I'd like to do some more examples of finding the radius of convergence. I'll do them in the next video. See me there.